do this and that and maybe that and all. Hi, lesser known math fans. Today I will show you something unique. You can read here who is the author of this paper, William H. Gates, Bounds for Sorting by Prefix Reversal. This is the Journal of Discrete Mathematics from 1979. And of course, this is not anyone else but famous Bill Gates, the co-founder of Microsoft and the richest man on earth for nearly 20 years before he was surpassed by Jeffrey Bezos. And of course, the co-author here of Bill Gates, Christos Papadimitriou, is not a random person, but a famous professor in theoretical CS. So here is what the Wikipedia page of Christos Papadimitriou says about exactly this paper. So Papadimitriou co-authored a paper on pancake sorting with Bill Gates. We'll see in a minute why this is the same paper. So yeah, then Bill Gates was a Harvard undergraduate at that time, and this is what Papadimitriou recalls. 2 years later, I called to tell him our paper had been accepted to a fine math journal. He sounded eminently disinterested. He had moved to New Mexico to run a small company writing code for microprocessors. I remember thinking, such a brilliant kid, what a waste. Anyways, that's a fun story, but if we go back to the actual paper, the title is something about sorting, and we mentioned that this is actually a paper about pancakes. So if you just scroll down here at the very beginning of the introduction, you see this paragraph, which is actually a quote from another paper. Basically, in this quote, Gates and Papadimitriou explained some interpretation of what they're doing, and this interpretation is related to pancakes. We are going to illustrate this pancake interpretation just by using these 4 pancakes. But wait, they must be of different sizes. Well, as a good waiter, before bringing my pancakes to the client, I would want them to be in nice order. So the largest one should be at the bottom, the second largest on top of it, then the third one, and finally the smallest at the very top. So my buddy, the restaurant chef, prepares the 4 pancakes, but he gives them to me in such a way, stacked on top of each other in some arbitrary order. So of course it would be inconvenient to ruin the current stack of the chef and just sort the pancakes by ordering them one by one, like that, maybe. Well, actually, this was not that slow. Perhaps I don't need the algorithm of Gates at all. But remember, I have just 4 pancakes here, so if I have 400 pancakes, maybe I will actually need the algorithm of Uncle Bill. Anyway, so I want to keep my stack of pancakes, and what I'm asking is, can I just sort them using flips of some of the top pancakes, like that? So for instance, I can take the top 2 and just flip them, or I can also take the top 3 pancakes and do the flips. Yeah, technically I'm allowed to take just the top one and flip it, but this doesn't make much sense. So at any given moment, I'm allowed to do 1 out of 4 different flips. So for instance, one way to sort these 4 pancakes would be just to flip the top 2, then to flip all of them, like that, and then just to flip the top 3. Okay, so there we go. The great benefit of this method for me as a waiter is that I can perform it just with one hand while I'm walking towards my client, right? So I can do this and that and maybe that and oh no. So actually, instead of doing this difficult business with the pancakes, I can just look at permutations of 1 to 3 up to n. The permutation that we looked at using pancakes was this one, 1, 4, 2, 3. and we actually performed 3 flips to sort it, right? So we first flipped this prefix to get 4, 1, 2, 3, and then we flipped everything to get 3, 2, 1, 4, and then we just flipped the first 3 elements, this prefix, right, to get 1, 2, 3, 4. So I can ask how many flips I would need in the worst case to sort some permutation. In other words, I can just denote by f of n the maximum number of flips that I will need to sort a permutation length n. And this is actually what the paper of Gates is looking at, some bounds about this f of n. So we have the trivial bounds for f of n over here. F of n is between n and 2 times n, and we can see this pretty easy. For the upper bound to n, just move this prefix ending at the largest element, and by that this largest element will go at the top, and then I will flip the whole permutation, so the largest element is going to go at the bottom. So kind of ignore this element till the very end and just operate with the remaining n minus 1. So this argument just shows that with 2 flips I can move one element at its correct position. Of course, if I do this consecutively, I will need at most 2n flips in total. For the lower bound, the situation is slightly more tricky, so I can just call 2 numbers that are consecutive and at consecutive positions adjacencies. And I can just observe that at the very end, when I have 1, 2, 3 up to n, I have n minus 1 adjacencies. So everywhere I have adjacencies. However, at the beginning, you can give me some permutation where I don't have any adjacencies. And the key thing is that when I perform a flip, I can increase the number of adjacencies by at most 1. This directly implies that for some permutations I would need n flips at least. We will see now how the paper of Gates improved one of the bounds. So the new upper bound that the paper obtains is this one here. F of n is at most 5n plus 5 over 3, which, as you can see, is slightly better than the upper bound of 2n. That is sort of obvious. And the way they get this bound, as I explained, is by analyzing their algorithm. The goal of the algorithm is to get permutations in one of these 2 forms. And to do that, basically Gates look at 7 or 8 different cases for the input permutation, and he basically see that whatever this input permutation is, we are into one of these 7 cases, and there is a way to get one of these 2 forms. So the key thing about permutations in these 2 forms is that if I have one of these 2 forms, then I can simply apply not more than 4 flips to get the identity. And at the end, let me also say that another reason for me to be that excited about this paper of Gates and Papadimitriou on sorting by these flips is that one of my first own papers is on a topic related to a similar type of sorting. It's called sorting with cuts. And just to show you what is this all about, I will give you an example. So if we have this permutation 2, 2, 1, 3, 6, 4, 5, sorting with cuts is just we go over the permutation from left to right, and we are allowed to select a given segment and then cut it somewhere in the middle, which means we pick some position and then we exchange the 2 segments on the left and on the right of this position. So for instance, here, if I go from left to right, I can pick this segment and then I decide to cut in the middle. So this would mean that I will get 1, 2 in the output. Then I skip 3 and then I select also that segment and I decide to cut over here. So 3 stays as it is, and then here after I do the cut, this goes on the left, this part goes on the right. So I will get 4, 5, and then 6, which is the identity. So in this particular case, for this permutation, I got the identity just by one single pass over the permutation, and I decided to perform these particular cuts here. So the main result of this paper of mine is that with this similar type of sorting with cuts, whatever permutation I give to you with n elements, you need at most n over 2 such passes in order to sort it. So yeah, I just thought that that would be nice to be included here. Okay, so that was everything from me. I have given a link to the paper of Gates, to my own paper on sorting with cuts, and to the relevant OEIS sequence for these pancake flips. Maybe here is the moment to say also that these fans of the conspiracy theories should not look at the paper of Gates and try to find the words chips or maybe vaccines there in order to show that Bill Gates had some secret plan back in 1979. So please guys, don't do that. And that was it. See you next time for more lesser known stuff.